Coming. For those who don't know me, I am Paul Eugenio, the President Chairman of the Physics Department. So it's really a pleasure to welcome our speakers, faculty, and we have a nice, a group of students here. So that's great to see. So for the Dirac Lectures, where we're, we have the series to honor the memory of Paul Dirac. Sort of, when I was asked to just provide an opening welcome, I sort of remembered when I first joined the department, and shortly, while I was still an assistant professor, we had a celebration of Dirac, the Dirac Centennial Symposium in 2002. And this was to honor the anniversary of Dirac's 100th birthday for 2002. So I went through and just, reviewed and looked through this. What I did find was interesting is on the very first sentence of the preface, right at the beginning of the book, which was written by a professor at FSU at the time, Howie Baer, it states, Paul Adrien Maurice Dirac, one of the icons of modern physics, began his formal work in new quantum theory beginning in 1925. So while we were celebrating the Dirac centennial, we could think of 2025 as, the opportunity to celebrate the Dirac quantum centennial. And what is interesting is in 1925, Dirac wasn't even studying quantum theory initially. As a student, he was he got a degree in electrical engineering, couldn't find a job, went back to school, got a bachelor's degree in mathematics, and then led into graduate studies in theoretical physics. And while he was initially studying general relativity, and it was his advisor who gave him a preprint, a pre-copy of Heisenberg's paper on the matrix formalism of quantum theory that really inspired his efforts to study, quantum theory. And from then on, he switched as a graduate student in 1925 to study quantum theory. Wrote the first, within a year, wrote the first PhD thesis on quantum mechanics. Shortly after that, created a new formalism that made the connections between sort of the classical mechanics to quantum mechanics, and a whole plethora of things within a short span. As we know, the Dirac equation, prediction of the positron, and so forth. So I say this to the graduate students that you can be inspired. You never know when your inspiration may come. It may just be one paper and you change your career and you can have a lasting impact in science. So with that spirit, I'm pleased to welcome our speakers and excited about the lectures that are going forward. So with that, now we'll continue the program. Thank you.
Okay. Thank you very much. Thank you very much, Paul, for nice introduction. So we are very fortunate to have three distinguished guests for this occasion. And the cosmology, many exciting things is happening. We don't know why, and I can tell you safely, nobody on this planet knows what's happening, but something mysterious happening to the universe. So we have three distinguished guests, Professor Licia, Verde, David Schlegel, and Adam Rees is going to be joining tomorrow. And the first speaker of today is Professor Licia Verde. Do you go by Licia or Licia?
Licia is the Italian pronunciation. Right. Outside Italy, nobody can pronounce my name, so Licia is fine.
Okay, so she's originally from Italy, and she graduated from University of Padua, where the Galileo Galilei was teaching, and got a PhD from the University of Edinburgh, and got the staff research associate position at the Princeton, where she overlapped with David Slidley, I think, for the Sloan Distance Sky Survey project. And she worked on many, many things. Cosmic microwave background, galaxy surveys, and she's the one who combined many surveys and get the cosmological parameters, and she pioneered this area. And she got the faculty position at the University of Pennsylvania, and then moved to the University of Barcelona, where she has a professorship right now. And she's got many, many awards, and please look up her Wikipedia, and including the Breakthrough Prize in Fundamental Physics. So she's going to tell us about the current status Lambda-CDM, which may or may not be true. Thank you.
Thank you. So thank you so much for inviting me to be here. No wonder that Dirac decided to go from Cambridge to here. There's, nothing to envy to Cambridge, actually. I do cosmology. That's what I love to do, is the study of the universe as a whole. And you may think that it's a little bit pretentious, but I would say it's relatively easy, because if you go to large enough scales, and if you want to study the universe as a whole on very large scales, then what happens is that all the forces that we are used to see here, they sort of cancel out. And the only thing that remains on very large scale end up being a relatively weak force, that is gravity. But since it's always attractive and doesn't cancel, if you go to large enough scale, that's what remains. And gravity is relatively easy to model and follow. And that's what makes it relatively easy to actually do cosmology on the largest scale. So this is a little bit the outline of my two lectures. We're going to start from the top. Everything, it's beautifully ordered. We all agree it's all concordance. And then we'll start going down. We'll have a ha-ha moment. And then, everybody and every has a skeleton in the closet. So we're going to discover the skeleton in the closet in the second lecture. So the part one will be the making of precision cosmology, and the part two will be beyond precision cosmology. So cosmology is looking up at the extragalactic sky to learn about fundamental physics. But learning about physics by looking up at the sky, not necessarily the extragalactic sky, it's not new. Starting from Galileo, who taught at the same university, but not at the same time, thankfully. Newton, and we have learned about the evidence of dark matter that says there is something beyond the standard model of particles. And we've learned about solar neutrino oscillations, and we'll see dark energy and inflation. Inflation is, I like to say, quantum in the sky. And I know you had some Dirac lecture about inflation a few years ago, so I'm sure there's some record of that, and you can find more there. So cosmology has an extremely successful standard model, which is the model we're going to discover today, which is the Lambda-CDM model. And sometimes the lambda becomes an L because we're lazy. And so this model with just 6 numbers describes the evolution of the universe and fit a whole series of completely different observations from the very early universe all the way to the development of galaxies, etc., and all the way to today. So these 6 numbers can be divided in sort of 2 types of numbers. There are numbers describing the composition of the universe that dictate the background evolution, their density of baryon, density of matter that is not baryon, cosmological constant, and the current expansion rate of the universe. We'll get back to that later on. And then some parameter describing the perturbation. In a completely homogeneous universe, we wouldn't be here. We are large perturbation compared to the background. And there are two parameters describing the statistical properties of this initial perturbation, and one effective parameter that is related to when the first star formed. So this describes the observation of the universe across some 14 billion years of evolution, and the model's parameters are now determined with percent error, and this is what makes precision cosmology. So precision cosmology was born in the early year 2000 and has been going very strong until today, I would say. And let's see if I convince you that maybe it's time to go beyond precision cosmology. So the cosmological model I'm going to talk about, it's not Dirac cosmology. Dirac cosmology, this is a letter to the editor of Nature signed by Dirac, wanted things like the gravitational constant to change in time. This is not what we are discussing here. The fundamental constant remain constant. The physics as we tested here today is the same physics that apply to the whole universe. And this is one of the pillars of how we go about to build the cosmological model. Even though, and you will learn from Professor Lee's lecture, the consequences of his cosmologies, you got a number almost right, which is the value of the Hubble constant today. So what are the pillars of the model? So the pillars of the model are, well, we have the standard model physics particle, and then the constant of nature are constant. We have gravity, GR, that describe the universe, gravity rules. We know how to describe gravity, even on the largest scales, even though today we tested it basically on solar system scale, and we are doing a massive extrapolation, but we work with that. And then is something called the cosmological principle. So the cosmological principle, it says that we are not in a special place in the universe. And so the universe is homogeneous and isotropic, statistically on average, because obviously it's not isotropic, otherwise and homogeneous, otherwise we wouldn't be here. It's like so statistically. And this has consequences. So statistics become extremely important in cosmology. Every statement we do is a statistical statement. So statistics doesn't only go into error analysis. It goes to when you measure something, there is always an error associated to it because you are making an intrinsic statistical statement. So this evolution of the Copernican principle brings you back, the homogeneity and isotropy, brings statistics straight into, from the very beginning of the name of the game. Means that we deal with summary statistics, because the model will never tell you that galaxy will form there, while that other galaxy will form there. And so we are forced to use summary statistics, not force. With big enough computer, we are moving beyond that, but there's some value in thinking about in this term, like the power spectrum and the correlation function. And most cosmologies are Bayesian, and I think it's because since you observe one part of the universe and you want to make inference about the model because of the cosmological principle, you have to imagine that if you were another one in another patch of the universe, you would statistically make a measurement that is consistent with the measurement you do here. Then you want to do inference about this universe that you can't see. You want to make inference about the model, and therefore you end up being Bayesian. And it brings in the fact that precision is not the same thing as accuracy. We know how to deal with precision. We don't really, at least in the Bayesian framework, know how to deal with accuracy. So open questions in the 70s and 80s is, well, we know the universe started off with a Big Bang. What powered the Big Bang? What made the universe homogeneous and isotropic on average? But non troppo, because some perturbation must have been there, otherwise we wouldn't be here, but not too big and not too small. And where do these small initial inhomogeneities come from? But again, you had some Dirac lecture exactly about inflation and about the quantum on cosmological scales there for you to observe and make inference on. And so this brings in another pillar, the hot Big Bang and inflation. It is this period of accelerated expansion where quantum fluctuation become classical and give rise to planet, star, galaxies, us. But also the dark matter. When we knew about the existence of dark matter since the work of Vera Rubin, since Zwicky saying that there's more matter than meets the eye, so we have to live with that. And then we were forced to include another pillar. And by the way, yeah, which is just give me a standard candle. So now here works on supernovae, and I'm sure you talked to him, and if you haven't, you should. Because this, I'm going to cut the story very short because the other lecturer, Adam Rees, is going to talk about that. But basically, if you have a standard candle or a standardizable candle, you can measure distances, and measuring distances in cosmology is very, very difficult. Because if you know how intrinsically luminous your standard candle is, depending on how distant it is, you know how dim, you can measure how dim it is, and then you can start making plot like this. Recession velocity, redshift, versus distance. And then you can start mapping the expansion history of the universe. And what came up of that experiment was that, look, the universe is actually accelerating, not decelerating as gravitation, as GR tells me, if there is matter in it. And so that brings another pillar to the model, which is the cosmological constant, which we call dark energy today, but it's very related to that. And that in 2011 was recognized with the Nobel Prize, of course. So here's the pillar of the model as the late 90s. And this was also recognized in 2019 by the person that actually built up this model, even without having all the observation that we have today, and still the model fit. So let me take a little bit of a digression because it's going to be important later. Cosmology is special because we don't make experiments. We tell the funding agency we make experiments, but we don't. We only make observations. And so we have to use the entire universe as a detector, but the detector is given and we can't tinker with it, in the word of Jim Peeble himself. Which has driven a massive experimental effort to observe as much as possible of the universe, make your detector as big as possible, and then you get more sensitivity. And the next lecturer is going to go through a lot of what it means doing this. So this is a mixed blessing. It's a curse, but it's also a blessing. It's a curse because we only have one observable universe, and we can only make observation and only of the observable universe, but not experiment. So we end up fitting model that is constraining numerical value of parameters to the observation. So almost any statement we do in cosmology ends up being model dependent. And in the middle, there is gastrophysics. This is not a typo. It means complex astrophysics that is poorly understood and hard to model. And no linearities gets in the way, but it's also a blessing because you can observe all there is to see, and we can always try to do that. So one important observables that was one of the milestones to actually confirm and build this standard model is the observation of the baby universe, as you can probably see, which is the cosmic microwave background. This is the relic radiation from the Big Bang. If today the universe was an adult, then looking at the light that comes from the cosmic microwave background will be like looking at the baby that has just been born. So I could go many lectures about this, but I will not. So I will try to give you a very fast story. So this is an early history of cosmic microwave background temperature measurement from Penzias and Wilson that saw a uniform glow, and that was what sealed the fact that there was a hot Big Bang. That's the relic radiation. To the next full sky map of the cosmic microwave background, the COBE satellite. This is the mission from our own galaxy. The universe is homogeneous and isotropic, but we live in a galaxy. That discovered the primordial fluctuation, the seeds of galaxies. to a whole suite of ground-based and balloon experiment, Toko Boomerang, Maxima, CBI, Akbar VSA, to the next full sky map, which is the WMAP satellite, again, higher resolution and better mapping of the emission from our own galaxy, which can be removed through multi-frequency information. And so this is what has been called the primordial firewall, the echo of the Big Bang, the surface of last scattering or recombination. So the universe was hot and dense, and of course, after removing the DC mode, the Penzias and Wilson, so. And the detailed statistical property of these ripples can tell us and told us a lot about the universe. So these are what they call the spot, corresponding to tiny ripple in density, the seeds of galaxies. So how is that? Let me run through it very quickly. So the universe back then was made of a very hot and dense gas, and it was emitting radiation. This is the radiation we see there. This radiation is uniform, but with tiny contrast, 1 part in 10 to the 5 in density and temperature. So these are ripples in a gas. These are sound waves. So we are really seeing sound waves. And in the world of Wayne New, this is a cosmic symphony. So this tiny fluctuation quantitatively, not just qualitatively, we know that gives rise to galaxies and everything we see today. So I like to make this parallelism. When Fermi was trying to sell the first particle accelerators, was saying, well, you know, we are smashing what we believe they are the fundamental particle with each other, and then we see what comes out. It's like smashing 2 grand piano together, and from the debris, figuring out how the piano is made. Here we do something different. We try to listen to the sound of the universe and figure out how the instrument is made. And this is something that we do all the time, right? Sometimes you want to know what something is made of. You go like this, and then you figure out what it's made of. Now you say, who is knocking that, and who is playing the instrument? Again, back to inflation, but I will not talk about that. So for the next few slides, I'm going to be inspired by this work by Paul Dirac. I consider I understand an equation when I can predict the property of its solution without actually solving it. So in order to understand how we can learn about the universe and precision cosmology from that picture of the cosmic microwave background, you need to solve a whole hierarchy of Boltzmann equations. We are not going to do that today. We are in TikTok time, so I'm going to give you, in the time of a TikTok movie, a very quick CMB theory background. So at the last scattering surface, we are seeing a snapshot of the photon-baryon fluid. You have photons and baryons. They were coupled because the photons were coupled to the electrons, and the universe was ionized. This, about 380,000 years after the Big Bang, it's a unique window into the early universe. So we'll not ask to put them there. We'll ask what's going on, just by observing what may have happened. So on large scales, you could only have the primordial ripple. On very large scales, outside the horizon, that's it. On small scales, you can see there are 2 competing forces. Gravity, that creates compression, and photons that have radiation pressure. If photons are coupled to the baryons, then you have something like this. The photon represents the spring, and the baryon represents the masses, and the primordial ripple represents this potential well. In here you have everything, even dark matter if there is. And you can imagine the opposite one on a potential hill instead of a potential well. And so this sound wave stops oscillating on recombination. When the universe cools down and the atoms recombine, at some point, the photons can't be coupled to the baryons anymore. The photons go away, they stream through, and then you get this snapshot, the snapshot of the baby universe. And so this gives you a fundamental scales, which is the horizon size of the last scattering surface, like a fundamental mode. You only have time to go through a compression, and then the thing recombine. And then overtones, like it happens when you blow on a pipe. Right? You have fundamental modes and overtones. And so what to expect Well, summary statistics, of course, and the summary statistic of choice is the angular power spectrum as a function of multiple moment, or actually angle. That's about 2 degrees. So on very large scale, you expect the primordial fluctuation. Then at some point, you expect to see what corresponds to the first compression. And then you have compression and rarefaction. Of course, this is a power spectrum, so it's square, so it also looks like a peak. And then a series of overtones. And then you go, how does this depend on the composition of the universe and the properties of the universe? And then you can change the geometry, how much dark energy there is, how much baryon there are, how much dark matter there is, and you can see that the curves are different from each other. So just go and measure it, and that was the name of the game. In the end of the 90s, that was the state of the art, and the lambda early adopters already appear at this stage. And then 2001, we can see a first peak. 2002, wow, now we can really start doing some cosmology. And then WMAP came along in 2003. And then at this point is, OK, move over. Now we can just really do something with this. And the result is we can really do parameter fitting. So we generate a lot of model, we do the likelihood with the data, and then we do the standard Bayesian inference. And this is from ADS, the trends of the world, Bayesian, Markov chain, Monte Carlo, and parameter inference as a function of the year. So that became the name of the game. Now, if you pay attention and you think like a cosmologist, you will realize that the result as shown is not really meaningful, and I'll let you think why. You are missing a bit of information there to make it meaningful. So let me move on. So I took this from the Nobel Prize printout of the 2011 prize to the discovery of the accelerating universe. And what they had there, it's this map with the constraint on the parameter of the model, and this plot that shows matter density, cosmological constant density, the cosmic microwave background as this long degeneracy in parameter space. The supernovae have this one, and then, oh, look, we are sitting there. So by that time, it's the first time that in the review of particle physics, a chapter in cosmology was included. And by that time, the particle physicists and the condensed matter physicists got convinced of the standard cosmological model. However, I hid a bit of information from this plot, because that was not sufficient from what I'm showing you here. There's another bit of information that convinced them. Two lines will always cross in a plane. So that's not enough. OK, so let's move on. Between early 2000 and 2010, we've been playing with precision cosmology, just 6 number, and the name of the game is just constrain this number to better and better and better precision within this model. Or see if there are parameterized deviation from the model, from things that we can think of come natural, or at least are easy to model, to constrain. And so these are called extension to the L-CDM model. Some of them are meaningful, like neutrino masses, number of neutrino species, curvature. Other things are less physically motivated, but why not? As long as you don't find any deviation, it's still useful information. So OK, so let's go back to this. What did we do? Well, in this year, we went on the blessing and tried to observe all there is to observe, which brings the idea of an ultimate survey. An ultimate survey means that if you do it again, a similar one, you would not learn anything new, because you already observe all there is to see. So if you observe it again, it doesn't matter. And actually, this has driven a massive experimental effort, and we did it. The Planck collaboration with the Planck satellite has saturated the information content of the primary CMB temperature anisotropy. Repeat the experiment. Maybe you can get a little bit more of information, epsilon information, but it will not be the CMB primary temperature anisotropy. So let's look at this. In the same scale, same map, just looking at the different resolution. COBE 1994, WMAP 2003, and Planck 2013. Look at the exquisite resolution. There are ground-based experiments that have much more resolution than that, but not over the full sky. But what I want to introduce is that after the first Planck release, there's another map that appeared, which is the map of the polarized sky. The CMB fluctuation is not just temperature, the CMB light is also polarized, and the polarization also has its own statistical property. And I want to measure very quickly how the CMB polarization is generated. Temperature quadrupole, because of Thomson scattering, at the surface of last scatter generates polarization. So if you have no quadrupole, no net polarization. But if you have a potential hill, which look hot, because the photon needs to run down the potential hill, and the potential well, which look cold, because the photon needs to climb out of the potential well, then you do get a net polarization. So repeat this pattern spatially, and you expect a radial pattern around the hot spot and a tangential pattern around cold spot. And this has been observed, so which is quite cool. This is by itself doesn't constrain cosmological parameter, but it's a very powerful consistency check that you're understanding what's going on. And I want to dig out something, an archaeological find on a slide from 2003, where we see, look, on large scale, there is an anti-correlation between temperature and E-mode polarization. And if you had a casual seed model or isocurvature initial condition rather than adiabatic initial condition, you will not have had something like that. This is a super horizon perturbation, and there is this anti-correlation between the velocity, which sorts the polarization, and the density, as it should, because they are anti-correlated. So again, this is a qualitative statement. You can make it quantitative, but that has implication for understanding what powered the Big Bang. Fast forward to 2018 and look at the precision of these plots. So the information content in the primary temperature anisotropy has been saturated with Planck, but polarization data is the key now to constrain cosmological parameters with a little bit more precision, angular resolution than Planck. A ground-based experiment get as much statistical power from polarization that they get from the density, and this offers also a wonderful consistency check. Again, unique window into the early universe. The upshot of this is that what you kept seeing over and over in all the paper coming out in the past decade or so are plots like this. What do you have? In each post stump, you have one parameter of the model, and in the other one you have another parameter of the model, and then you have a lot of way to combining the data and say, I take this and analyze it this way, I take that and analyze it this way, and you end up having all these color ellipses or bananas, and then they keep shrinking. So every paper that come out later, it looks the same except that you change the scales. So this has brought historian of science, Tim Maudlin, to say more has been discovered about the large-scale structure and history of the visible cosmos in the last 20 years than did the whole prior of human history. I think we should be proud about this statement, pat in the back. Okay, so far so good. But what about the other 13+ billion years of cosmic evolution? We only look at the baby universe, what happened in between. And so the other avenue has been exploring the lower redshift universe. So if these are the initial map of the initial perturbation, and if it's true that on very large scale, basically there's only gravity after recombination, then we have computers that are powerful enough that you can simulate gravity. You put a lot of particles in a box, and then you just let it evolve. And n-body simulation over and over show you that, well, on the linear scale, you could do it analytically. On mildly nonlinear scale, you can also try to do it analytically. It comes to the nonlinear scale, the computer is much better than you. But this is matter. Not everything shines. What we see is the galaxy distribution, which is something like that. And in the lecture by Professor Schlegel, you would know how a map like this is generated. The only thing that you need to know now is that the simulation is a box, but if you are sitting here and observing out of the galactic plane, then you of course are going to observe two cones. You don't want to observe extragalactic sky through the galaxy. Good. So the establishment of the standard cosmological model was built and started when the state of the art was something like this. And then it moved on over the next couple of decades with the slow and digital sky survey to something like this, where that like fit in a corner here, and then you keep on going and you get something like that. And yet, it still all hangs together with just the same 6 numbers. Well, you had to add extra parameters because the theory tells the distribution of the dark matter. You observe the distribution of the galaxies. The two may not be exactly the same, but grosso modo, that's what it is. One way to actually understand where a lot of this information come from the baryon acoustic oscillations. So a lot of the information enclosed in the large scale structure, not all of it, but a lot of it, is enclosed in this signal. Let's figure out what this signal is. So remember this, when we say we observe a photon coupled to baryon, and you're seeing a snapshot of the photon-baryon fluid, and you have a characteristic scale, which is the sound horizon at recombination. When we look something like this, we see dark matter. Well, dark matter is the scaffolding, and then galaxies form on this scaffolding. But as baryons are 1/6 of the dark matter, this baryonic oscillation should be imprinted in the dark matter because gravity is the coupling. How does the imprint look like? So this is how the imprint look like. It's a series of oscillations, but since they are very small, because baryons are a fraction of the dark matter, to see it, I have to plot the power spectrum divided by a smooth power spectrum, so then the oscillation can be seen. So let's see if the animation goes. So imagine you had a single perturbation, and then the perturbation is there, and in the oscillation you see photons and baryon couple, the photons run away, the baryon go with them, and then when the universe cool at the last scattering surface, then you get something like that. Like happen when you throw stones in the pond. But now you should imagine a superposition of those, of many of those, that do exactly the same. Like throwing stone in the ponds, but all the stone at the same time, and not one before and one later. And again, this is related to inflation. And you should see something like this, therefore, statistically on the galaxy clustering on large scales. And again, it's a nice connection between what's happening at the last scattering surface and what's happening at several different snapshots along the life of the universe. So this, by its construction, it's at one given snapshot. And so the information is exquisite, but it's limited at one screen. While in the large scale structure, you can repeat that, give enough people like Professor Schlegel to actually build the instrument to actually observe this at several different redshifts. It's a little bit like seeing the same fingerprint later on in time and know which one is the culprit. So this is called the standard ruler, because it's the same physics that you know very well from the early universe that gave us the oscillation of the cosmic microwave background seen later. Well, actually, we see it in 3 dimensions, not in 2 dimensions. The last scattering surface is a 2-dimensional surface, but this is a 3D. So it's actually a standard bubble, maybe, but that's OK. We still call it standard ruler. And let's recap. The sound waves in the early universe propagate until decoupling. This in part are scales, that is a standard ruler, which is a key observable, useful for learning about the geometry of the universe, the expansion history. The early universe physics, which we say it's well known, sets it. And early universe physics plus observation of the cosmic microwave background in a standard L-CDM model gives you the standard ruler length to 0.2%. That's precision. The first detection of this came in 2005. There were back-to-back papers from the 2-degree galaxy redshift survey and from slow and digital sky survey. One analysis in Fourier space, the other analysis in real space. The signal to noise was excruciatingly low. You can see it by eye, but the points are correlated. But this is beautiful. Bang, you expect it, and it's there. It's where you expect it to be. And then everything else is history. But before we understand why everything else is history, let's go through and see what this feature actually measures. So if you have a standard bubble out there in the sky, then the first thing you know is, OK, if it's farther away, it subtends a smaller angle. If it's closer by, it subtends a larger angle. Notice that all that you observe are angle and redshifts. Your theory, it's in distances. So the very first thing you do, whenever he gives us a survey, we just go and transform it into distances. And to do that, you always assume a model. Because the redshift to distance, angle to distance, you have to assume a model. So what's going on? Well, if you have the right model, what's an isotropic signal remain isotropic. But you don't have the right model, because otherwise, why do you do experiment in the first place? And so if you don't have the right model, then you get an isotropic effect. It could be that thing looks squashed this way, or it could be that things look squashed this way. So, but you say, well, does it mean that I lost all possible constraining power? Well, no, because you do know what model you use, what fiducial model you use. So with respect to the fiducial model, this is actually signal. This is not noise. So I can know how far away I am from the fiducial model that I chose. So the power of the BAO, that is always a relative measurement compared to the underlying fiducial model. And it's done based on templates, of course, because of the nature of the signal. So you don't have only the overall size of the BAO, but you also have an anisotropy signal. And this is the classic Alko-Paczynski. And you can also repackage it in 2 other things, the transverse signal and the line of sight signal. Of course, these 2 are not independent from these 2. You can always combine these 2 and get this, and combine these 2 and get this 2. But sometimes it's more useful to think in this term, and sometimes it's more useful to think in these terms. So for the aficionados, the parameters that you introduce are alpha iso, the ratio of the size to your fiducial model, and the distortion, which is the classic Alko-Paczynski, or the ratio on the parallel and perpendicular with respect to the line of sight. So this is related to distances. How is this related to distances? Well, when you measure the line of sight feature, you are measuring the distance, the line of sight distance. And here I have for the aficionado the equation of what is the h. The h is basically 1 over the Hubble at that redshift. And on the other direction, you measure an angle, you interpret it in terms of an actual distance, then you have this other distance, dm, which it's written here And if the universe is flat, you don't have this bit, and you have an integral over the 1 over the Hubble parameter along the line of sight. And of course, it's always relative to a fiducial model, and it's always relative to the size of the standard ruler, which is RD. This RD is not exactly the same as the sound horizon at last scattering. It's a little bit later. It's a radiation drag. But the relation between the two is so tight, it's very difficult to think about something that could give you that as a mismatch that effectively is the same physics that gives you both. If you know one, you know the other. So it should be clear that this tests only the background. The test is only the expansion history. It doesn't test the growth of the perturbation, which is still included in the clustering, but we are throwing away that information. And therefore, we are only looking at linear background quantities. And here they are in all their beauty as the data kept pouring in on the correlation function on this side and on the Fourier space on the other side. In order to see it better, you need always to subtract something smooth, because the signal otherwise, percentage of the total signal, it's small. And it's so beautiful that by the mid-2010, getting into the 2020, this is from the entire saga of Sloan, including BOSS and extended BOSS, you can do a plot like this. The measurement with respect to the measurement that you expect, given the prediction of the model as you've seen it in the early universe. And it looks with a wonderful agreement there. So what are we doing here? This is basically a little bit like doing distances, right? And we did distances, we talk about distances with supernova. So one is a standard candle and the other one is a standard ruler. They both measure distances with different underlying systematic, underlying physics, underlying assumption. But mostly, this one is calibrated in the early universe, and this one is calibrated here today. So you see where I'm going. So you're doing a distance ladder. Now you can extend the distance ladder all the way to the baby universe. So if you are doing baryon acoustic oscillation, you take the standard ruler from here, you go to the BAO, you figure out how they are aligned, how they are shifted with respect to your fiducial model, you get your relative distances, and then you can infer quantity today. With the supernova, you were calibrating today, getting the parameters of the model, and then extrapolate it to the entire universe. But by then, the redshift distance and the statistical power of these two probes started being comparable. So you could also calibrate one to the other one and basically interlock these two distance scales, which is quite cool. So by now, you should have realized that we've done two slightly different things. When we were analyzing the cosmic microwave background, we were taking the data, a model that is a function of the cosmological parameters, and directly fitting the summary statistics and getting plot like those. This is called the direct or full modeling. But when we were doing baryon acoustic oscillation, we were not doing that, were we? We were doing a compression. So we were taking the data and then taking a template given by the fiducial model, figuring out how was the alignment between the template and the summary statistics, and then working with that quantity, that alphas. That's a compressed variable. It's a massive data compression. We always do data compression. The summary statistic is a data compression, and it's not a lossless data compression. This is also not a lossless data compression, but by design. Because you just want to extract a feature from the data with the help of the template, and you want just to extract what your signal, which is the angular location of the BAO, not its amplitude, not its exact shape, not the broadband. There are pros, there are cons, and we should discuss this later on. And the calibration of this is given by the early time physics that gives you the length of the standard. Okay? So with this, one can do an Hubble diagram with the BAO, exactly like you would do an Hubble diagram with the supernova, and then plot like that started being produced as part of several compilation of surveys. So now you can understand what I hid from this slide when I show you for the first time. I hid this. So by that time, the baryon acoustic oscillation were known only in a relatively small redshift range, and so it had a degeneracy in this parameter plane. And then what happened here is that the three lines in a plane is not guaranteed that they cross all in the same point unless you're onto something. And it was that, I think, that convinced the particle physicists, dense matter physicists, that actually the cosmologists were on the right track. And this is not just about shrinking the error bar on some cosmological parameter. This is more a qualitative statement than a quantitative statement. So I know what you think. You say, okay, but you did Dirac fit for the cosmic microwave background. You did compress variable for the baryon acoustic oscillation. Is that a mismatch? Can you do better? Yes, of course you can do better. You can also do Dirac fit with the larger scale structure. But the pristine, pure, simple information is enclosed in the summary, in the compressed variable. But you can do that, and it gives you a very consistent story. So then you can combine and do joint analysis of clustering of both ends of the universe, and the parameters of the model end up being measured with 1% precision. So things like the amount of matter in the universe, the age of the universe, and such. Let's step back a second. This is better than medicine can determine somebody's age. Your height is not known better than 0.6% or comparable to what your height is known, because your height changes during the day. Your weight can fluctuate as much as 5% in a day. The square footage of your house is imprecise at the 1 to 2% level. The police speed radar are imperfect at the 2.3% level. Yet the current error on the expansion rate of the universe is quite competitive with that, but I let Professor Ree's lecture explain why and how. And without that for the entire universe, within a model, of course. So you can see that we are here. Everything works, everything is wonderful, we have everything under control, and somebody called it a maximally boring universe. Is it a maximally boring universe? I think boring is good. And all cosmologists will agree that boring is good, because now you can do precision tests of fundamental physics with cosmological data, because you have something that works. And then you can actually do precision and say, if I modify the neutrino property, if I modify the dark matter property, what's going to happen? So assume a reference L-CDM model, and then add parameters that give you control, small deviation, perturbation from this base model, and constrain those, and hunt for departures. And so things like dark matter, dark energy, nature of gravity, physics of the early universe, neutrino masses, they all come down from the maximally boring universe. So boring is good. So let's recap. By the end of the 2010 and dawn of the 2000, we had the maximally boring universe. The standard cosmological model survived ever more stringent tests. Deviation from it, even more constrained. So we all knew from the back of our mind that eventually something will have to give, because the model is simple. We don't know what's lambda, we don't know what dark matter. I mean, it's an effective model, it works extremely well. Eventually, it would have, something is going to give. The point is, how much smaller would the observational error bar have to be before we realize that something has broken? But in the meantime, we party like it's 1989, and we started doing precision physics with that. For example, neutrino mass is within the reach of the next generation of experiment of larger scale structure. And so that's what we did. So we started having plots like this. This is from the EBOS collaboration. Now, this is again density of matter versus density of lambda. And now the cosmic microwave background has become this. And the supernova has that. And the baryon acoustic oscillation has become this. By adding enough snapshot at the different redshift, the one that seems to be a degeneracy this way has been broken. Each redshift gives you a degeneracy, but the degeneracy turns. So put enough redshift, and this starts breaking. And again, you have wonderful agreement. And then you start playing games like this. So you move along the cosmic microwave background degeneracy for deviation from the Lambda-CDM model, curvature, property of dark energy, mass of the neutrinos, and then you say this model, and this model are all consistent with the CMB and the Lambda-CDM model. Can I see how they look like for baryon acoustic oscillation? And you will see that some of those models are even outside of the plot. So that's how you constrain deviation from the base model. The base model is still pretty much in agreement. Temperature and polarization.
Yeah, but I mean, does that look very consistent with all these?
So this is maybe not even 2 sigma. Remember, we are doing a statistical statement, so 2 sigma could happen. I mean, 1 out of 3 times you're supposed to be outside the 1 sigma, so it's okay. At this moment, nobody was losing sleep over that. But watch that space. So in the past few minutes, I want to give you an example of what it means doing precision physics with cosmological data. And I want to talk about the cosmic neutrino background. So we know there should be a cosmic neutrino background. It's a relic of the Big Bang, similar to the CMB, but it decoupled from matter at 2 seconds, not 380,000 years. The coupling neutrino is still very relativistic, where they have large velocity dispersion. They still today are supposed to be hot. They have large velocity dispersion. Remember, matter radiation equality, it's around 1 eV, and recombination is at 0.26 eV. Now, if you stuck your thumb out, you have about 60 billion neutrinos per second coming from the sun. These are not the cosmological neutrinos. There are only 100 from the cosmic neutrino background, but these one from the sun are localized around the sun. The universe is very big, and so despite this density being much lower and much lower energy, this is much higher energy, this one are the ones that matter cosmologically. So let's talk about neutrino mass limits. Neutrino oscillation tell you that in this plot, the mass of the lightest neutrino versus the sum of the masses of the neutrino, you have 2 possible hierarchies. Up here, they are called degenerate. They're never degenerate, but in this plot, they look the same. And then they open up, and this is called inverted, and this is called normal. Direct measurement, for example, by the Catherine experiment, here it is in all its beauty when it was being installed. From tritium to beta decay, they measure the electron-neutrino mass, and their latest constraint of the total number of neutrino masses is up here. And their projection, when they finish running, of detection versus 90% limit falls in here. How does cosmology play in? Well, neutrino of a total mass above 1 eV become non-relativistic before recombination. So the effect is seen on the CMB. Very easy. Total mass below 1 eV become non-relativistic after recombination. This still alters matter radiation equality, but the effect can be cancelled by degeneracy. Unfortunately, the CMB is at 1 given snapshot, and therefore there are a lot of parameter degeneracies there. What matters is that after recombination, finer neutrino masses, I mean, they do that always, but especially after recombination, they suppress the matter power spectrum on scale smaller than the free streaming length. you can imagine that if you are a neutrino, you don't want to be trapped in a potential well. You run out. And by running out, if you have a mass, you take some mass away from the potential well, and therefore you erase perturbation below the free stream in length. And this is the typical plot that you find. The power spectrum, as you change the neutrino mass, respect to a power spectrum for 0 neutrino masses, which we know the neutrino have mass, but let's keep working this way, you do have a suppression. Now, this is if you keep fixed the physical density of matter, the physical density of baryon, and lambda. But you can't do that, because you need to move along the degeneracy of the parameter that is dictated by the cosmic microwave background. So if you do that, if you move along that degeneracy, and I do that by playing a lot with H naught, so H is everywhere, this curve that looks like this ends up looking like that. In reality, you get something in the middle. The CMB degeneracy is not infinite, so you get something in the middle. OK, so the BAO is useful to break the degeneracy in the background dysfunction history, so that you break some degeneracy in the CMB, and you can constrain the neutrino mass because you do something between this and that. So the situation in late 2010 was the following. All this bit was excluded by cosmology. Depending on which data set you look up, how you combine it, if you believe which colleague you believe, and how they propagate the error bar, the constraints land here and there. So the inverted hierarchy, according to some, is under pressure, according to others that are more conservative, not really. But this is obviously a window opportunity, because all the forecasts were living down here. And so the forecast was telling you, you may actually be even able to detect this, which will be good to actually look at the signature of neutrino from the sky. So cosmology is the key to determine neutrino masses. For the pessimist, the inverted hierarchy is under pressure. For the optimist, if it is an inverted hierarchy, then the measurement is just around the corner. We just need to agree, everybody, with the error analysis of all this data, and we can just do it. So far, the too long did not read. Cosmology over the past 2 decades has made the transition to precision cosmology, has moved from a data-starved science to a data-driven science, has now a standard model. The standard cosmological model only needs few parameters to describe origin and composition and evolution. The parameters are measured with 1% precision, but there is a big difference between modeling and understanding, and this implies challenges and opportunities. So if I have another 2 minutes, I'm going to give you a preview of what's going to come next class, next lecture. So if, as you do that, the model becomes very rigid, and you really tie rigidly all the observation by this model. In terms of cosmological parameter, you can imagine them as a target, and the target becomes smaller and smaller and smaller. And it's like basically trying to thread a needle from one side of the universe to the other one, with the eye of the needle getting smaller and smaller and smaller. So for 2 decades, smaller and smaller eyes of the needle were being threaded successfully. By the mid-2010, a new observational tool became competitive, which is called weak gravitational lensing. I will not spend a lot of time on it. Let's just say that you can use as background light either the cosmic microwave background or faraway galaxies. And because the matter perturbation in the middle bend the space-time and light goes along geodesic, the matter in the middle will distort the background light. If you know the property of the background light and you observe it distorted, you can infer what's the clumpiness in between. And the clumpiness is parameterized by the amplitude of the perturbation, the amplitude of the clumpiness. The amplitude of the clumpiness get enclosed in a parameter called sigma 8, the RMS fluctuation on a scale of 8 megaparsec. And this has been acting up lately. The low redshift universe seems to prefer a lower sigma 8. It's at the 2 sigma level. Maybe we shouldn't worry about the 2 sigma level, but a lot of ink has been spent on this. And remember this, right? And I'm sure Adam Rees in his lecture will show you something like this, which goes along under the big headline of the Hubble tension. Direct distance ladder, inverse distance ladder, that's calibrated on the CMB, that's calibrated on today, were more or less agreeing until about here, and then they started not agreeing. So now you know why I put a ladder there. So never a dull moment, and never mind that the model is weird. So to conclude, I think we are here where this guy starts saying, do you see what I see? And so I'll just put my credits on, and I'll stop here. Thank you.
Okay, thank you very much. So questions? First from students.
So I have a question about that. So
Could you repeat the question for the microphone conference?
they pick up yeah. So my question, I think they get. Okay. So you have a REBAO line which is completely degenerate with lambda, omega lambda, right? So could you explain again that how you break the degeneracy and that it's tilted to the other way?
Yes.
Yeah.
Yes. So very good question. So what if you have a distance at a given redshift, that dm or dh, what you actually by that time you had a combination of the two because there was not enough statistical power to measure the distortion. What you have is basically an estimate of omega mater at one redshift. You don't have the evolution of that. And therefore, in that plot, lambda versus omega mater, you have a perfect degeneracy. Because that redshift is not zero, obviously, it's the redshift where you observe the BAO. You need enough volume, because this is a feature of 100 and something megaparsec scale, so you need huge volume, and they don't exist at redshift zero. As the data started becoming better, and one started to be able to break the redshift bins, then you start having the entire omega mater at different redshifts. And then you can break the degeneracy. At any redshift, you have a degeneracy, but start rotating, depending on the redshift, and put enough redshift together, it breaks.
Maybe one more thing related to that. When you actually divide by fiducial model, is there any special meaning about this fiducial model, or this is just how you just know? I want to see that.
So there is not a special meaning about the fiducial model. You could choose any fiducial model you wanted. You need to declare what your fiducial model is, because unless you go a long distance in trying to keep working with redshift and angle, which make things very complicated, you always want to work with distances. So the first thing you do when the data come off the telescope, you transform redshift and angle into distances. You need a fiducial model there. And you may as well use the same fiducial model to actually say, with respect to my fiducial model, where is the scale of the BAO? You could use a different fiducial model for the template. The equation becomes a little bit more complicated, but you could use any fiducial model to do that. Of course, in detail, if you want exquisite control on the error bars and you don't want to have to run too many simulations of your survey, the closer the fiducial model is to the actual model, the simplest is the data analysis. But in principle, it doesn't have to.
Thank you.
So I think that Catherine just reported a very nice limit of like 0.45.
Yes, per one neutrino. So if I want the sum of the three, I need to multiply by 3.
What is the current limit from cosmology?
Aha. It depends who you talk to. And it depends within which model, and it depends on your priors. So until before the DAISY result, the best limit was at 90%, 0.6 0.7 eV. 67. 0.067.
Oh,
0.067. So it was right at the limit of the inverted hierarchy. With DAISY, this limit is stronger. But at that point, it matters whether your prior is neutrino mass is above 0 or neutrino mass is above 0.06. What sort of prior do I put? Do I put a log prior? Do I put a linear prior? Do I change the model, so I only add the neutrino mass to my model, or I also add curvature, different type of expansion history, so then it really starts becoming more complicated. But yes, you can ask, what happens if cosmology really tells you that the neutrino mass is 0?
Or negative.
Or negative. What do we do? Which is a very interesting question.
Towards the end, you showed you talked about sigma 8
Yes.
problem, where it looks like sigma 8 is less than what you expect. But I also, if I remember correctly, neutrino mass effect was also keeping around the same scale, of 8 megaparsec. So does the fact that there's a problem with sigma 8 put a doubt on the neutrino mass measurements about it?
This is a wonderful question.
Like how should I believe neutrino mass bound when I know that there's a problem around 8 megaparsec?
This is a wonderful question. So the constraint on the neutrino mass that the more conservative, say, constraint on the neutrino mass, the one that gets you to 0.1 eV modulo desi, comes just from the BAO. So this comes in microwave background plus BAO, so just expansion history. It doesn't care about the sigma 8 that we see today. So you could say, well, maybe the weak length sigma 8 determination is affected by some of the astrophysics that we don't know. The information come a lot from non-linear scales. Who knows what happened on non-linear scales? And leave it at that. But you can also take it seriously and say, how can you keep telling me that you get constraint on the neutrino mass within a Lambda-CDM model when the Lambda-CDM model starts telling you that maybe it has cracked because of the Hubble constant and because of sigma 8? And that's also a completely, a very good answer, question. Yes, something that we should definitely
Did you say
keep in
the
mind.
bound is 0.1?
So if you, before this, if you look only at the background expansion without adding information about the growth of perturbation, the limit was getting 2.1-ish at 9.1-ish. The moment you added information about the growth of structure, especially Redshift space distortions, then you could get to 0.067, 0.08, at the 90%. So start getting interesting. And the inverted hierarchy seems to be under pressure at that point because the inverted is 0.1.
Thank you.
Any questions? Steven? So if I may, so we're going to be discussing discrepancy in the next few days. And first of all, you're on the double map team. And when you saw the Planck team, there is a slight discrepancy. So what was your reaction when you see the discrepancy? Do you blame the measurement or do you blame the models?
Right, so I think the Planck team did a wonderful job when internally they saw that something was going on. So they started comparing the maps, going back to the map, to the time order data, to the summary statistics, and at the scales where the map were signal dominated, the Planck map are consistent with the W map. In the very, very, very first release, there was one channel where things were not really completely under control, but then that got fixed pretty much after that. And if you remember, when the W map result came out, we knew that the larger scale looked weird. the axis of evil and the alignment of the multiple and the cold spot. Somebody even saw the signature of Stephen Hawking in the sky. Things happen. And on the large scale, there's a lot of cosmic variance. There's cosmic variance because we want to infer things outside the visible universe, and we only see the visible universe. On the largest scales, statistically, you cannot know very well what the entire universe is doing. And the discrepancy between the model and the observation was mostly on those scales. So when Planck came along, Planck added a lot of statistical power on smaller and smaller scales. And the smaller and smaller scales look a lot like the Lambda-CDM model without the largest scales. But now you have two tensions. Right? The large scale that are low wants a lower omega matter, higher NS, things like that. And the small scales wants a higher omega matter and lower NS. And so depending when you stop, you're going to end up with slightly different cosmologies. But Planck found this inconsistency also internally. It's not that this inconsistency with W naught. And they went through years of work trying to simulate how much is the internal inconsistency. And it all boils down by 2.5 sigma level. And there's more than one thing that is on the 2.5 sigma. If these two things are related, it's just statistical. If these two things are related, then you sum them together, and then you have more than 2 sigma, and then you start worrying. And we are stuck there with some 2.5 sigma something, which could be statistical or could be not. And as far as we know, adding more data, it's not going to help, because we observe all there is to observe. If we repeat, we are not going to improve the statistics. And so we have to live with that. So there's no answer to your question. Some oddness is there, but we have to live with it.
So let me end with my question. So you mentioned that this is the maximally boring Lambda-CDM. So when the excitement started, in your opinion? Is that second lecture?
That's the second lecture. To me, the excitement started at a conference in 2019 when we were discussing the Hubble constant determination. And you have one side that does one distance ladder that says, look, I'm looking for mistakes, I'm looking for error, the data are public, the covariants are public, go redo it yourself. I'm getting this number. And then the other side that says, the data are public, the software is public, you can analyze yourself, this is the number I get. And the two numbers started not really being in agreement with each other. And we tried as much as we could to say, well, maybe it's neutrinos, maybe it's the polarization, maybe it's this, maybe it's that. And by that meeting, we just said, Houston, we have a problem.
Okay, that's the second lecture.
Yeah.
Okay, thank you very much.